Hello and welcome again. We have been discussing the two proton, two electron problem, basically two hydrogen atoms being brought together from a large distance, and we claimed that represents a two atom solid with one electron in each atom. So that is of course a caricature of a real solid, and we will soon take a step towards n equal to any number of atoms, and then we will see what happens. Let me just recap the salient features that we came across while doing this. What we did was that we first took a Born-Oppenheimer approximation, which means that the two atoms, their nuclei are more or less fixed in position, and the nuclei, the motion of the nuclei is not considered. So this this approximation is called the Born-Oppenheimer approximation, and under this approximation one basically neglects all the dynamics concerning the nuclei. That is again the same thing that we will do for n equal to n arbitrary number of atoms. The argument there is even stronger. If the atom has a z number of nuclei, then z number of protons and neutrons in the nucleus, then of course it is even better for us, because the mass of the nucleus is very large and the dynamics is very slow compared to the electronic dynamics. So that is the assumption, first assumption that one takes. So one looks only at the electron interacting with the nuclei. Remember that in this approximation electron interaction is neglected. So it is still a single particle description. We do not have an interaction term between the two interactions, two electrons. So what we did was that we considered a single electron, for example, with two interacting with two positive nuclei. We could as well to take two non-interacting electrons interacting with two nuclei, which is the same, because we are in a single particle description. So we will basically find out the final set of orbitals and put as many electrons as there into each of these orbitals, starting from the lowest. So this is the Hamiltonian that we wrote. The T is the kinetic energy of the electron. V1 and V2 are the electrons interaction with one nuclei at 1 and 2 locations, 1 and 2. So this is the picture we drew. So this you may call 1, this may be called 2, and these two, then the electron which is outside, the electron that we are talking about is interacting with these two nuclei. So that was the Hamiltonian we wrote. Then of course we argued that one more important thing is that there is something called a trial wave function, a variational principle in which a trial wave function is chosen, and that trial wave function is optimized with respect to the parameters in the variational parameters in the wave function, so that we get the lowest energy solution. That lowest energy solution is called the variational lower bound of the energy, and that sometimes agrees with the ground state, sometimes does not, but it is still a very good method to get a low energy eigenstate of a quantum problem. Now the approximation that one does is at the level of wave function. Now one chooses a trial wave function with say the electron at orbital at 1 and the orbital at 2. So these are the two wave functions we have, and then as I said, remember that 1 and 2 do not necessarily have to be orbitals of atom 1 and on atom 2, but that is one convenient choice one can always do, and one also remembers that these are not necessarily orthogonal, but to a first approximation we choose them to be orthogonal. So, these 1 and 2 are my two orbitals sitting at site 1 and at the location of proton 1 and proton 2, nucleus 1, nucleus 2, and then I can solve for this Hamiltonian by calculating the expectation value of E, which is the variational energy, which is defined as psi h psi divided by psi psi. This choice that with coefficients u1 and u2, which I chose to be real, is a linear combination of the two atomic orbitals, and this is in chemistry parlance called the linear combination of atomic orbitals. The name is quite obvious that we are choosing linear combinations of the two atomic orbitals. There could be other choices, there are other ways to write things, but this is a trial wave function which is very common. As I said, it is called the LCAO, linear combination of atomic orbitals. So, let us the matrix elements are very simple. T plus V1 is basically the first hydrogen atom and its wave function more or less, and so T plus V1 operating on 1 will give you this single particle hydrogen like energies, and this is the one. If I choose 1 to be 1s orbital, then epsilon naught will be basically minus 13.6 electron volt. So, nevertheless, as I said, I do not have to choose, but let us just assume that we know the wave function 1, which is an eigen function of T plus V1, which is the Hamiltonian for the first hydrogen atom. Similarly, for the second hydrogen atom number 2, the T plus V2 is its Hamiltonian, and this will be 2, sorry, this is 2. The second wave function is a eigen function of that Hamiltonian with the same energy, because there is nothing to distinguish between the two atoms. So, this is how we started, and then we assume that 1 2 equal to 0 and 1 1 equal to 2 2, these are orthonormalized. So, this is how we started, and then we define different matrix elements. So, let me show you these matrix elements. These are the matrix elements. So, this Ij equal to delta Ij gives me this is the same approximation as this one. So, energy, variational energy is given already, this one. So, minimization involves the parameters as we wrote. So, ui equal to 0. Since we have two u's, we will get two equations, and these two equations we already obtained in the previous class. So, let me just quickly, so therefore go ahead and remember that this is the energy T plus V1 between 1s, k bra 1 and k 1, the expectation value of T plus V1 is basically epsilon naught. V2 does not contribute to this one, so that is perfectly all right. I could as well, so this is basically 1H1, which is the 1 1 element of the Hamiltonian matrix. Similarly, 2 2 element of the Hamiltonian matrix is also epsilon naught. So, the Hamiltonian is epsilon naught in the basis of U1 and U2. Now, H12 is the Hamiltonian matrix element between 1 and 2, and this does not give any contribution from the first term, because it is this part is the diagonal part of the Hamiltonian. It will not have a cross term, and this is the term 1 V1 2 or 2 V1 1. These are basically these are called the hopping terms. This is the term that allows the electron to move from orbital 1 to orbital 2, atom 1 to atom 2 when they are brought close together. and vice versa, of course, from 2 to 1 as well, and they are not necessarily different, and it's convention to choose T and T star. One is just the Hermitian conjugate of the other. This could also be taken to be real. So there is I in the previous class I took them to be real, both as T. Otherwise I have to work with just mod T. Now there is this term which is 1 V 2 1 equal to 2 V 1 2 is basically V cross term was set to 0, because as such it is the effect of nucleus 1 on orbital 2 and nucleus 1 V 1 on orbital 2 and effect of nucleus 2 on orbital 1. These are anyway small, and the other important thing one notices is that this actually is cancelled by this nucleus interaction R1 minus R2, which is repulsive. Remember, these terms are attractive because these are the 1 V 2 1, this V cross is an attractive term, whereas this is a repulsive term. So this basically cancels that term. So I just do not have to bother about these are diagonal elements. Remember, these are contribute very little to the Hamiltonian, to the energetics. Okay, so this is the matrix that we are going to consider. So our equation of motion, the equation is basically then E times U1 U2 equal to epsilon naught minus T. This minus is just a convention. Let me take to be real, take this to be real, epsilon naught. This minus is explicitly taken here because in most of the cases this matrix element T turns out to be negative. But this is also quite clear that this should be negative, because if this is the, you will just see that this is the energy lowering that happens, and if it is it's basically the matrix element between the two this matrix element 1 V 1 2 and 2 V 1 1. So 2 V 2 so 1 V 2 2 1 V 1 2, all these matrix elements or vice versa for V 2, these are basically the hopping. As I said, it takes the electron from site 1 to site 2, or proton 1 or atom 1 to atom 2, or atom 2 to atom 1. So that is the way it gains energy. The system gains energy, delocalizes. The electrons gain energy. Okay. So the T here is positive. The negative sign is already taken care of. So this is my equation of motion. So this is basically Schrodinger equation written down here. So we diagonalize this, E minus epsilon naught square equal to T square, right? So the matrix, this matrix is basically E minus, I can bring the left hand side on the right, and this will become E minus epsilon naught square. So E equal to epsilon naught plus minus T. So as I said, this is the gain in energy. So we started with 2 epsilon naughts which were degenerate, and we landed up with 2 eigenvalues which are here and here. So these are my epsilon naught plus T and epsilon naught minus T. So that's so I now what do? I have now I have to put 2 electrons in the system. So these 2 electrons will now go here, and my gain in energy will be minus. Basically, original energy was twice epsilon. Let me choose the color. Original energy was 2 epsilon naught, and the final energy is 2 epsilon naught minus 2 T. So, this 2 T is the amount of energy that I gain by forming a so called molecular orbital, right. It is a combined orbital of the two atoms, and so the electron, basically both the electrons try to gain energy from this, and remember that this is the lowest energy state is a singlet. So, that means the orbital part of the wave function is 1 by root 2 u1 plus u2, which is the symmetric wave function. The excited energy, this is called the bonding, this is called the anti-bonding. So, the bonding is this one, the anti-bonding will be just the other combination. So, the symmetric one is the bonding one if T is positive. That means I gain energy by doing this. Okay. So, how does the orbital look like? Let me just show you first how does it look like. Starting, if I had started from just 1s orbitals, this is how the picture is. I had two electrons to start with, here one, and there are these two orbitals that have formed. They are conventionally in chemistry, they are called sigma 1s and sigma 1s star. So, this is the bonding orbital and this is the antibonding orbital. Look at the nature of this wave function. The orbital part of the wave function is symmetric here around the center, and that symmetry basically reflects the fact that the spin part is a singlet and the electrons are now equally shared by the two nuclei. And so, what is happening? What has happened basically? What has happened is that because of this T matrix element, the electron is no longer stuck at either atom 1 or atom 2. So, electrons are now allowed to move. Remember, if you had a time dependent Schrodinger equation. So, in the time dependent Schrodinger equation originally, these are stationary states, epsilon naught and both the epsilon naughts, two atomic states were far separated, then there is no chance for the electrons to move from one side to the other, and they would be stuck to their individual orbitals, which in this picture, for example, on the left in this picture are these two 1s orbitals. But now, once the two protons come close by, the electrons start talking to each other, then of course, this time dependent Schrodinger equation this allows now for the electrons to reside part of the time in the first atom, part of the time in second atom. That means it can hop over between the two atoms, two protons, and it is a state which is a linear combination. In this picture, it is a linear combination of these two atomic orbitals. So, these off diagonal matrix elements always do this. It allows you to have a state in which the electron resonates between the two atoms. If you have a multiple atom, we will show soon that it will basically now start resonating between all the atoms, which basically means that the electrons are now getting free from its parent nucleus. Here, of course, it is still attached to its parent nuclei. The two nuclei have formed a hydrogen molecule, and with the two electrons they had. So, and the antibonding orbital, as you can see, puts the electrons in the middle there is 0, that means that is the r equal to 0 point. That means it is putting a node at r equal to 0. Two electrons are the orbital part is the antisymmetric part. So, two electrons are not going to be at the same close to each other in the orbital part of the wave function. So, there is a node at r equal to 0. Remember your particle in a box. Particle in a box wave function was like this, right. See the the first ground state is this symmetric, whereas the excited state is has a node at the origin. So, this is the same picture. This is not exactly the same, but it is similar picture that we are getting here. We have a the excited state has a node at r equal to 0, whereas the orbital part of the ground state has no nodes. It is a symmetric wave function. Now, of course, this picture that I have just shown you with this Hamiltonian and diagonalizing it to get these two wave functions, two eigenenergies, E plus minus E plus minus equal to epsilon naught plus minus t, t positive again, remember. So, this energy, see here is mod t, because I had taken complex t star here. So, their product is mod t square, but if I take just t as real, then mod t is basically t. So, this in picture, what does it look like? How does it look like? So, if you look at this left hand side picture, the energy as a function of the distance between the two nuclei R12, in the bonding case it goes like this, in the anti-bonding case it goes like this as a function of R12. So, it is clear that the bonding one is the lower energy. This is bonding, this is anti-bonding. The problem here is a bit more complicated in the sense that although this gives me right energetics, it is not entirely correct as you go down to R12 very small. And why is it not? Because you can see that the electrons in this picture will finally come down to R12 equal to 0, this point. So, this is R12 equal to 0, this is the energy it will have. So, this is not correct, because the solution is not that the two nuclei just merge to form that will become a helium nucleus. So, that is and that we showed is not that is very different from a hydrogen molecule, right. So, that is incorrect solution, although this predicts it. Where does it go wrong? So, well, it goes wrong in the sense that there are several approximations we have taken. One was, for example, the orthogonality. Now, the orthonormality of the two wave functions, they do not remain orthogonal as R12 becomes small, because then there is a lot of overlap between the two wave functions, and you cannot neglect the non-orthogonality of the two wave functions. The 1s character of the wave function, for example, atomic character for example, will not remain as such. So, you have to consider non-orthogonal wave functions. That is one issue. Then there are these other V cross terms that we neglected. The other major thing that we neglected was this interaction between the two nuclei. So, if I had this is the interaction between the two nuclei. Suppose R1 and R2 are the electrons. So, if R1 and R2 are their coordinates, then this is the interaction that that we'll have to consider, and so therefore neglecting that interaction entirely will obviously give me a wrong answer. So, what is the right answer? The right answer is shown in the bottom picture. The picture is like this, that this is the antibonding and this is the bonding. Okay. So, there is a finite length distance here somewhere where there is a minimum in the energy, and as R12 becomes closer, of course, the energy becomes very large. So, that had to be the case because Coulomb interaction basically diverges if R12 equal to 0. So, there has to be a minimum somewhere in between, and that is exactly what this kind of a picture gives you. So, this is the antibonding and this is the bonding, and this is where the stable distance at which the nuclei will settle down. So, so this is basically the picture that emerged from the previous calculation and that we have been doing, and this is a picture that we will now go beyond it, and we will try to find out the case for large number of atoms, but our approximations will remain the same. These approximations work fairly well in a solid because of two major things. One is that in a solid, particularly in a metallic solid, there is the electrons are highly mobile. We know that, right? It has a very large conductivity. Electrons we find, we know that the velocities or speeds are large, and so they are not delocalized. And one of the advantages of delocalized electrons is that any Coulomb interaction gets screened out very quickly within a short distance. So, the Coulomb interaction is much weaker than in an atom, particularly electron-electron interaction, one nucleus interacting with a neighboring electron. These kind of interactions are not going to be very relevant for the for a solid, which is particularly a metallic solid, where atoms are located at fixed distances, and this they are heavy atoms, and they are electrons can freely move about in the atoms because of this matrix element T that we wrote down. So, there will be T's, there are large number. I mean, in principle you can have now a number of T's, which is one electron interacting with its neighbor, next neighbor, next neighbor, and so on. These are all possible choices that one has depending on the material at hand. So, that makes life actually simpler in the sense that interactions often in metallic systems particularly do not play a very major havoc, and one gets nice beautiful pictures of bands that emerge from such calculations.